Okay, so now we're going to start to look at actual reactions and how we can change these hydrocarbons and organic molecules we've been working with up until this point. So just so we are under, so we are clear, there's not a whole lot of reactions that happen with alkanes. The ones that do happen tend to be fairly complex, and because of that, they aren't covered in IB. Um, the ones that are going to be covered in the IB model are going to be mostly those of alkenes. And a lot of this is either going to be electrophilic addition, or the other option that we're going to be looking for is nucleophilic. I've touched on this really briefly before, but just remember when you see this word electro, it means negative charge or electron, and then philic just means love. So you're looking for things that are going to love the negative, and then nucleo just means positive. So when we have an alkene, what's happening is we have the sigma bond, which is the very first bond that gets made, and then we have a pi bond that happens on top of this. This is where the double bond is actually happening. We get this hybridized orbital so that we have a pi bond between those two carbons. When we end up having an addition reaction, the pi bond is the one that's going to be broken, not the sigma. Examples of different electrophiles, these are going to be things that have a positive partial charge, so they're looking to find negatives. They love negative charges. So here, this side right here, this hydrogen in this model, is going to be the electrophile. The opposite side, this one, is going to be my nucleophile. I bring this up now because we are going to start to see some nucleophiles, and it's just good to think of it ahead of time. The most common ones are going to be hydrogen halides, so HBr, HI, HCl. All of these are going to be great electrophiles for additions, and then also concentrated H2SO4. This is just a very strong acid. So when we have electrophilic addition, what actually ends up happening is this. The double bond of the pi, it splits up, so this breaks, and one of these electrons, both of these electrons jump up and make a connection to this positive, and then this electron pair that is keeping the hydrogen halide together moves over to the halogen itself. Because hydrogen can only have 2 electrons in its orbital, what happens is the other bond breaks heterolytically, meaning it splits in half. The H attaches to one of the carbon atoms, and then we end up with 1 electron over here. So one of these electrons is going to jump onto the hydrogen, and the other one is going to just stay there as a carbocation. We're going to see the actual mechanism for this right now. So you start to see this carbocation right here. And a carbocation is just a carbon that is a cation, a carbon that is positive. This is an incredibly reactive species. This carbocation does not exist very long. In fact, what ends up happening is when this bond splits right here, and you end up with this H plus and Br minus, the lone pair from that Br minus, we can see it right here, serves to create a bond between the carbocation. And then we can see that bond happening right in this area. So it's creating a bond on that carbocation. We use this, we actually call it nucleophilic attack. So you can see it acts as a nucleophile and attacks the carbocation using its lone pair to form a covalent bond. So what we've done is we've split up this double bond, and we've added a hydrogen and whatever the halide is. In this case, it ends up being, it looks like a bromine. So we add a hydrogen, and I'm going to just write halide. right here we can see the full mechanism as it plays out. So these two, first off, this bond will break and it jumps over here to create this negative, so we end up for a very split moment an H plus. This is my electrophile. And it's going to seek out these electrons. Those electrons are going to serve to create the bond here, and then that creates this carbocation here on the ethane. And then the bromine uses its lone pair to create the new liquid, and we end up with bromoethane. So here are step-by-step, I guess, instructions for how this works out. So we have HBr nears the alkane, and it's got to be very close for this to happen. So the hydrogen and the bromine don't split when they get into solution. They'll stay together until they get close enough for this reaction to happen very quickly. The electron attaches to the slightly positive end of the H, and then the HBr bond breaks immediately when that happens. So when the electrons jump over to the hydrogen, before the electrons actually make it there, right before, you get this bond breaking and creating it over there. Hydrogen cannot hold more than 2 electrons. It just doesn't have the orbitals, so that's one of the key rules in organic chemistry. And then the bromide, since it is negative now, this ends up acting as a nucleophile. It's going to start to look for the positive. And then there is the positive charge, and it attacks the carbocation, and it uses that lone pair to create a covalent bond. What we have here is it's just an animated mechanism for how this is happening. So you can see what's happening first, and then next up what's going to happen. So these bonds are breaking almost simultaneously, and then the bromine is going to join. I'm going to wait for this whole mechanism to play out before we move on. And that's that. Another way that we can have an addition reaction without the use of HBr is if we have a Br2, so this is just 2 bromines, as they orient themselves and approach these double bonds. This double bond actually has a fairly high density of electrons, making this area negative by nature. So what we get is an induced dipole. As the bromine approaches, you get this partial positive on this side closest to the double bond, and the partial negative on that side. As it gets closer, it actually gets to be strong enough to break this bond and end up with the same pattern we saw before, where the bromine is now a nucleophile because it is negative in charge, and then this first bromine would be our electrophile. So it should look very similar to the one we've seen before, except you just need it to get close enough to induce the dipole so that it splits up. And then here's the full-blown explanation. What I would like for you guys to do is, I'm not going to labor on this. I talked about it on the previous slide. If you want to read it, it's just step by step, so you can write it down. IB expects you to just really memorize the reactions, from what I can tell, not the mechanisms behind them. So don't worry too much about diving deep into this. One of the things that we actually use this for, and the way we can see how this reaction is happening, is we put some bromine in the test tube, and then we add in a hydrocarbon. And then this is a good way for us to test if this hydrocarbon here, if this is an alkene or not. Oops, A-L-K-E-N. So if we're wondering if a hydrocarbon is an alkene, we can put it in there with some bromine, shake it up. If the brown color disappears, that means that the bromine was used. It was completely used up. It was the limiting reagent, if you will. It has added on. So if it disappears, then the hydrocarbon's an alkene. If not, then it wasn't. It would have been an alkane. Another group that we can actually use to add on, or another group that we can add on to an alkene is this is how we can add alcohols, so add an OH group to these alkenes. And this is the way my organic chemistry teacher explained this to me was, quote, sledgehammer chemistry. We are using concentrated sulfuric acid at an 85% solution. This is incredibly strong. I've seen it once in my life, and the second I opened it, you could see the smoke start to come out, and it was just because it was breaking down into water and then SO2, and you could see that gas start to release. So it's incredibly strong stuff. This is an intermediate step, this area right here. This is an intermediate step. What that means is it is only used as a vehicle to get us to this final spot. So you should see that this concentrated sulfuric acid, it starts here and it ends up in the products. So it starts as a reactant and it ends up in the product. So really it's basically a catalyst. The only thing that we are using up in this whole process is we are using water. We're trying to get that OH and the H to split up in water, and that allows us to add on the OH and the H to break up this double bond. So you can see that we've added an H here and an OH group. So there's the water that we've added on there. This is basically the same process that is used in fermentation. So when you're turning, when you're creating ethanol, or basically alcohol. It's the same process, but just sped up because we're using the sulfuric acid as a way to speed it up. It's basically a catalyst. So far, we've only looked at these types of reactions in terms of ethane. So in terms of C double bond C with H's coming off of it, only 2 carbons. What ends up happening is this is not very frequent. In organic chemistry, you end up with much longer chains with double bonds in between 2 carbons that aren't terminal, meaning they're either going to be secondary or tertiary carbons. So then what ends up happening is you have 2 different ways where you can produce the product. You can produce the 2 possibilities, one where you end up with a 2-bromo propane, or down here this would be an example of a 1-bromo propane. Where the hydrogen in this situation, the bromine is going to join the second carbon, or if it's down here in this example, the bromine is going to join the terminal carbon. So then we have to figure out which one of these is going to actually be the case. Which one of these isomers is correct? These are structural isomers of each other. Meaning they have the same chemical formula. The only thing that differs between them is their structural setup. They're set up in 3 dimensions. We are able to move a bromine from one carbon to a completely different carbon, so we can draw them differently. Then we start to talk about Markovnikov's rules. He was really the first person to crack the code of the alkenes, and he found out, and this is just one of the many, many rules of organic chemistry you're starting to learn. The major product is formed on the more stable carbocation ion. So what that really means is the least stable is going to be methyl, which is just a single carbon. The next least stable is going to be primary. Remember, that's a carbon with one other group attached to it that is not hydrogen. Secondary is then next, where we only have 1 hydrogen attached to this. In primary, we have 2 hydrogens. And then tertiary, where there are no hydrogens attached to this carbon, attached to the carbocation ion. So this is very important to keep in mind. This is why I introduced the idea of primary, secondary, and tertiary carbons early. And I'm going to hammer that home more on Friday when we continue to wrap up our worksheet. I'm going to have you start to identify which one of these is primary, secondary, and tertiary, and then how do you know? This rule is going to come up and it's going to help you get the right answers more often than not. So then the way that we can actually see how this happens is the future functional group, so in this case the bromine, is going to join, oh, that's not how you spell join. This is going to join, it's going to add, oh my goodness, my spelling, the more stable carbocation. This doesn't happen 100% of the time. It happens more frequently than the other ones. So in this situation, it could join, this would be a secondary carbon, and this would be a primary carbon. And what it's going to do is it's going to join the secondary carbocation more often than not. So this here, the bromine on the secondary carbocation, is going to become the major product, and the minor product is going to be the one right down here. So then on this slide, I just kind of wanted you guys to see the two step-by-step possibilities that could be formed by following Markovnikov's mechanism. So the very first one, you're just going to see this being the secondary carbon getting the nucleophilic attack. And then down here, and then you can see this is the 2-bromo propane. And then down here, this is where the primary carbon is going to get it. And we are also going to end up with a 1-bromo propane. 2 is going to be our major product. And the first one, 1-bromo propane, is going to be our minor product. We are going to end up with more 2-bromo propane than 1-bromo propane. Another way that we can do these types of reactions is if we want to add in another OH group. So this is another example of how to add an alcohol group. This is the only difference is the situations. So in this one, I need high pressure, and we're going to be using gaseous water, so steam. And it's going to, we also need to use phosphoric acid. So this would have H3PO4 somewhere in here, but it's only as a catalyst. When we are looking at our other way with the H2SO4 to add the alcohol, this is not technically a catalyst because it gets used in an intermediate step. But in this situation, phosphoric acid is a true catalyst. It's going to just facilitate. So the reason why we need to use all of this extra effort is because OH bonds are very strong. And this is because if you have OH bonds, they tend to make hydrogen bonds with each other. And that's just a big problem because they want to stay together. They have those hydrogen bonds which are incredibly strong, especially with OH because O has 2 lone pairs and it's polar enough to create this partial positive over here and a partial negative over there. So it's just an incredibly strong species. They tend to stay together very, very tightly. So next up we have hydrogenation. And this is just when you're wanting to switch an alkene to an alkane. So basically what ends up happening is you have C's, 2 H's on there. And then you have your hydrogen there. And this nickel serves as a good oxidizing agent. It's a good way to serve to break this bond. And then you end up with the same type of situation where this hydrogen will jump on this carbon and it'll take these electrons with it. You end up with the carbocation here, and these 2 electrons are going to go there. And you end up with this H- that immediately latches on because H- is not a stable species at all. H- is not happy. It's going to jump onto the carbocation as soon as possible, and then you end up with ethane, C. This is just something that you're going to have to remember. This also tends to need high heat, just a way to help facilitate it, give the molecules more energy so they're moving around faster, so they're going to hit each other more often with more force. So it's just hydrogenation. It's a way to make a double bond a single bond, really. Polymerization. Polymerization is one of the greatest things that humans have ever come up with, and it's also one of the worst. Basically, what ends up happening is we form incredibly long chains based off of one repeating unit. That one repeating unit is called a monomer. So this is a repeating unit. When it repeats multiple times, so like a polygon is a side with multiple, or shape with multiple sides, a monomer, mono meaning one, turns into a polymer, poly meaning many. So you're going to end up with the same shape over and over and over. It's just you're having something and it's going to react with itself. All of the atoms are used in the polymer, so you're just going to keep adding in the same thing, and you end up getting some of the most incredible stuff that we've ever made. So you'll see polyethylene, polypropylene, and the way this will end up working out is you're going to have this unit repeats over and over. So if I was going to draw the next chain of a polypropylene, it would be carbon, 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 over and over and over. I'll draw this out in class just so I have enough space to show it all to you. But this is stuff like PVC piping. Those plastic pipes that are used in houses all over the place now. That's what it is. Here is Teflon. It's just a carbon with fluorines all over it. And it repeats over and over and over. So these are just fluorines. Tetrafluoroethene. And this is the stuff that's on pan so that when you're cooking eggs, it slides off really easy. Polymers are plastics. Polymers are IV tubing. Polymers are, if you look on the faucets on your house, if they have plastic little nozzles on it, that's some sort of polymer. Bags from Billa, polymers. It's all polymers. It's crazy. It's all carbon, hydrogen, oxygen, and some sort of other organic molecule on there. So polymers are made by a free radical process. What that means, this free radical, is if we have bromine and it gets hit with the perfect wave of light, so this would be UV light, that light has enough energy to split the bond, but not one way or another. So it actually breaks evenly. So this would have, they each would have a lone pair of electrons again. We use the same technique to split these bonds as well in the polymer, because remember, a polymer has to have a double bond. It's going to show up, and then the sigma bond still stays, but the pi bond gets split up again. And then if this happens to the carbon atom next to it, what ends up happening is, and I'm going to draw it sideways here, when this bond gets split again, we have single pairs, and then we get this chain starting to form. This carbon is going to find the next free radical, and then this carbon is going to find the next free radical. We get these very long chains, incredibly long. So now what happens is the physical properties, they get varied by changing the reaction process. So if we use more temperature, pressure, they also have the overall physical properties. So when you're looking at the macro level, like IV tubing compared to a hard plastic PVC pipe, what's actually happening there is the functional groups. They have a large say in that. So the chemical properties are based off the functional groups of their structure, but those chemical properties propagate up into the macro level where you can start to see physical differences in them as well. And then because they are a very large alkane, they are inert. They do not react readily. Remember, alkanes are pretty tough to react with because it's very nonpolar. It's hard to get anything in there, and they're all single bonds. There's no way for us to use any sort of electrophilic attack, and then that electrophilic attack lets us do a nucleophilic attack afterwards because we have a carbocation. Since they are all single bonded, it's really hard for us to start to facilitate that process. So what that means, it's resistant to a chemical attack and it's non-biodegradable. This is why people aren't a big fan of polymers. Like plastics take forever to break down. It's just one of the downsides, but the upsides are we wouldn't have a lot of what we have with our lives right now without polymers. Polymers are incredible. So polymers, like I said before, they've been wonderful for us now. They're invaluable in modern society, but their disposal is the biggest issue. We don't have a really good way of chemically or using bacterial means to break these down. And then because of that, they just kind of add to the landfill. We just throw them somewhere, bury them, out of sight, out of mind. So there are a few ways that we've tried to solve the problem. One of them is recycling, but it costs a lot. It's very, very expensive to recycle in terms of energy, in terms of manpower, in terms of chemical usage, so that's kind of a lot. We could burn the waste, but the problem is that's producing energy, and whenever you're burning waste, you're adding to the greenhouse problem again. We have these fumes that are coming off that are either going to bounce off the ozone layer and come back down to us, or they're going to stay in the ozone layer and serve as a reflective surface for light. So it's just going to trap more heat in our system, our ecosystem. Or else we can just produce gaseous HCl. Like, nobody really wants to breathe in hydrochloric acid, and that's one of the things that could happen as well. And then lastly, we got feedstock. Basically, feedstock is a way of chemically recycling. So the old way of recycling would be to just break them down into a liquid and then reform them, maybe repurpose them. Feedstock, what we're doing is we're using other organic compounds and new technology to take these and turn them back into hydrocarbons. And when they're back into hydrocarbons, we can turn those hydrocarbons back into alkenes, and then we can take those alkenes and then turn them back into polymers. So this is like the chemical way of recycling. This is more feasible, but it's also pretty expensive as well.